All right, welcome. So I promised to talk about the identity behind teleportation. So we'll do that for the first bit. Then we'll talk about how to generalize it to qubits, d-dimensional quantum systems. And then we're going to get into Bell's inequality. It's also called CHSH Game. This is another very important theorem, the fundamentals of quantum mechanics. It's not there in the book with Sumit, but it's there in my prior book. So if you want to look at the reference, I'm going to upload notes that I have online about it. Just to remind you, in case you didn't realize, I am uploading all of my notes to the course website along with the videos. So, I see some of you taking very careful notes. That's good, right? Just letting you know in case. All right. So, first of all, are there any conceptual questions about teleportation that we talked about last time before we start into the math? I tried to address various questions, natural questions that have come up in the teleportation discussion. So let's go through this. So the initial state is this tensor product. And phi is short for phi 0, 0. So let's make a shorthand. Okay. And psi is alpha 0 plus beta 1. So let's write that out. Alpha 0 plus beta 1. And then this one is by definition. All right. Then tensor product, work it out. We get bring the 1 over root 2 to the front. First step, simple enough. Remember, we view this as expanding the state in the Bell basis of A prime and A. That's the main idea behind the identity. So to do so, we can use these identities right here. Right? So we'll substitute in for 0, 0 this, and let's just write it out. Each of these has a factor of 1 over root 2, so we'll bring that to the front. A and B. This one. Just plug it in. Finally, this one. Okay. Now we just find matching terms, right? So we're going to pair up the phi terms that correspond to each other. Phi 0, 0 with phi 0, 0. Let's do it. Another step of algebra. That's this one. 5, 0, 1. No, we'll do 5, 1, 0. Beta gets a minus sign. Now the B gets flipped. And we'll write the final term. One. Questions about that? Just using algebra of tensor products. Right. Now the next key thing is to realize, so psi is alpha 0 plus beta 1. So the next realization to make is that each of these others are Pauli rotations of the original state. Okay, so we can get this state right here by applying z to the initial state. Right? And then once we have that, the identity is done. Right? I'm just going to suppress the systems for this final rewrite. This is z on psi. This one you can see is what we call bit flip, right? So 0 and 1 get flipped. That's understood as x acting on the original state. Then here, this one I'm trying to forget. So x and z. You can see it by examining this, right? So this is what you get by applying z to this, and then if you apply bit flip to this, you get this. That's the identity. Right? So that's what we skipped last time at the end. And just to remind you quickly, once you have this identity, you realize, oh, if Alice does a Bell measurement on A prime and A, you have it here, here, and here, then you would get one of these 4 outcomes with uniform probability independent of the state. So it's like a universal teleporter. Right? And then you get one of these 4 possibilities. Before Bob gets the classical information, his local state is a maximally mixed state, right? That's what we talked about. So there's no teleportation that's occurred until the classical signals reach Bob. And then once the classical signals reach Bob, he knows, oh, okay, psi, it's z psi, x psi, this one. And then he can apply a Pauli to undo it. Okay. All right. Let's talk about the Q generalization of teleportation. So for this, we have the Heisenberg-Weil operators. We defined these previously. We don't, to do this analysis, we don't, the way I'll do it, we don't really need to know precisely what these are. If you want to see an alternative analysis where their precise definitions are used in the analysis of Q teleportation, take a look at the book. Okay, all we need to know is that they're unitary and they're orthogonal with respect to the Hilbert-Schmidt inner product. What does that mean? If we define YZX to be WZX tensor identity phi. Phi is the canonical maximum entangled state. So the main thing that we need to know is that these states are orthogonal to each other. They form an orthonormal basis. Okay? And so that's the qubit version of the Bell measurement. Right? Here, this was the Bell measurement for qubits. This is consistent. These are consistent if d equals 2. And then you use this for higher dimension, for finite dimension, arbitrary finite dimension. Okay, so let's analyze the protocol for teleportation into this. Okay, so similar kind of picture, except now this is a qubit state, and this is the maximum entangled qubit state, all right? So we assume they share that. Then Alice performs a Bell measurement. Okay. And there are two outcomes, Z and X, each of which are, we follow this terminology, we would say classical bit. Bit means binary digit. Bit means d-ary digit. Okay. So what I want to do to analyze each of the outcomes is to just use these diagrams that we were using before. Okay. And I want to reason in terms of this transpose trick. It's a very powerful equality that we use a lot. Just to remind you, the transpose trick is this. And the transpose is with respect to this basis. Okay, so it's a little weird, right? Like, but this is how entanglement works. So if Alice does a unitary, so M is an arbitrary matrix, right? We think of it as square. You do have a generalization when M is rectangular, but let's think of it as square. So the way you interpret this is that if Alice does a unitary, then it's as if Bob did the transpose of that unitary on the maximum entangled state, right? Even if they're like very far apart. So that's kind of weird, and what Einstein called spooky. Similarly, if this were a projective measurement operator, if Alice does a measurement, it's as if Alice does a measurement and gets a certain outcome within this post-measurement state, it's as if, this is the post-measurement state also, and it's like Bob did the measurement. Okay? But there's a difference there. Alice needs to know the measurement outcome, right? Or Bob needs to know the measurement outcome to know the post-measurement state. So anyway, this is an identity we'll use. So how do I want to use it? I want to analyze this kind of diagram. So if we get a particular outcome, these correspond to Kets. So the way that the diagram goes is the opposite order of the math, right? We make the time go from left to right. The math goes from right to left. This is to respect different cultures in the world, right? So, okay, so these are Kets, is the point, right? And we want to project on, when we do this measurement, we project onto a bra. So why don't we write out the math, okay? Here's phi, a prime. The math looks like this. And then we're projecting onto a prime. Right? And this is the same using definitions. We take the dual of this vector, we'll get W deck, right? So phi a prime a W dagger ZX. Okay. This is a prime. Okay. Now, sorry. So the diagram corresponding to the math is this, WZ dagger, and then this is a projection onto the maximum tangled velocity, right? And okay, I think this is fine for that. How can we use the transpose trick? Show this stuff. What can we do with the transpose trick? It allows you to bounce the operator around. That's why people also call it ricochet tricks. Right? So what I want to do is bounce it here, because there's a maximum entangled state, and then bounce it again. Right? So that we can do. So you can do it with the math or with the diagram. Right? And a second. Okay, so let's write what happens if we take the dual of this. We get phi m dagger is phi m conjugate, right? Because if we take transpose on conjugate transpose, that's just complex conjugate. Right? So because this is a bra, we have to use the dual. Entity a prime tensor CX conjugate. This is acting on A. Psi A prime, phi AB. Okay. Now we go back and we use this one. So we bounce it over to B. So, you know, to do this one, in the math, I bounced it off of 5 onto A. And now that it's on A, I can use this ket to bounce it on system B. Psi CX. And then we take the transpose of the complex conjugate, we get conjugate transpose. This is on system B. Okay, so in diagrams, what are we doing? Right. And then that's one bounce, and then the other bounce is this. And good. So now, this is on system B, so it can actually be, you know, these vectors correspond to system A prime and A. So in terms of the diagram, you can see that we can do this commutation, right? So like this part can kind of be, anyway, you see it, this is just like the identity, so we can just drag it along, right? That's fine. So let's do that in the math. And then we're left with analyzing this. And this we actually analyzed before. So if you look at the overlap of, we're looking at the overlap of this maximum entangled state with a valid projection, right? What does that evaluate to? Previously we said, oh, you just pull the lines, right? And then you get the identity map. So, that's how you can think about it. And it's just like a channel from A prime to B with WZX dagger. Let's work out the math so you can see it. So if we take phi A prime A, I believe we did this calculation before. We'll just do it again because it's fast. Okay, using definitions, this phi will have a 1 over root d. This phi will also have a 1 over root d. Let's bring it out to the left, 1 over d. And we'll write this as I prime I A. We're left with j on A, j on B. Do some exchanges. Then you get a delta function with the A's. So we're matching up the corresponding systems. Right? Technically, to be totally precise, I would have to take this vector, this bra, and tensor it with an identity on B. Okay? And this one I'd have to take and tensor with an identity on A prime. But I'm doing that implicitly. All right? If you work out all the dimensions of the vectors and matrices involved to get a proper combination where the matrix multiplication dimensions worked out properly, you would need to do that. Okay, but I'm kind of skipping that. All right. And this becomes a delta function, and then we're left with 1 over d. Delta function, so the j is equal to I, b prime, b. And then I finally claim that you can rewrite this as an identity channel. It is as an identity matrix where the input is A prime and the output is B prime. Yes?
At the top, between the first and the second one, are you suppressing some identity on the B system?
Many identities are suppressed. Yeah. So, yeah. This is a good question. To have everything proper, we should write let's just do it from the beginning. I'll just rewrite this line properly. I think that's all it is. Tensor identity on B, psi A, phi. That is fine.
I was wondering how you did the second ricochet basically without
Yes.
an identity on B.
But it was there. Yeah, good question. Okay, so using this identity, we can then say WZX dagger on B, and then the 1 over D, I'll bring it out front, and then identity going from A prime to B psi A prime, and then we'll do a final rewrite. That's 1 over D WZX dagger psi on B. That's the final collapse, right? So what is all this saying? With the Q-to teleportation protocol, this is what we start out with. We do a bell measurement. We want to know two things. What are the post-measurement states and what are the probabilities of the outcomes? We can figure out both in one go if we calculate this overlap, right? So we calculate projection of the state onto one of the measurement outcome possibilities, right? Then, while this math, we get to this. So what do we find? this part right here is a normalized state vector, right? So that is the post-measurement state. And then out in front is the probability amplitude of a particular outcome, right? So with probability 1 over d squared, we have to square this probability amplitude. Remember, with the Bell basis, z and x each go from 0 to d minus 1. So there's d squared possible outcomes. Okay, so that's what we expect for a uniform probability for the outcome. So with probability 1 over d squared, the post-measurement state is WZX dagger psi. So now what? In the protocol, Alice just sends the outcome, and then Bob knows, each of these are unitary. That's the key property we need. So Bob can just invert this unitary, apply WZX. And then the teleportation is successful. So that's Q to teleportation. All right. And, made possible by the transpose. All right, so now we have plenty of time to talk about Bell's theorem, unless there are questions about this. So Bell's theorem is one of these funny things, like came out with it in 1963 or 1964. And the work was basically ignored for a long time. You can read this funny book called How the Hippies Saved Physics. And it tells you how like the only people studying Bell's theorem in the 60s were like, these people on psychedelic drugs in the Berkeley, San Francisco area. It was called the Fundamental Physics Group, and it's spelled physics with an F-Y-S-I-K. To look like kind of funky and weird or whatever. Anyway, so then, but much later, it started to be taken seriously. And then in 1982 was when the first experiment was done to test Bell's theorem. This was Elaine Aspect, and this is why people think he should get the Nobel Prize. I mean, it's great. It went to people who are understanding climate change. It's wonderful. Maybe at some point, even in the distant future, it'll go to something like teleportation and time. Anyway, and then it really started taking hold with the advent of quantum information. So in 1991, there was a scientist named Arthur Eckert, I believe coming from Oxford. It's either Oxford or Cambridge. And he came up with a method for key distribution based on Bell's inequality. And then that was like this fundamental link between Bell's theorem and something very practical. So like link the foundations of quantum mechanics to the practical idea for communication. And then you can see that, I mean, nowadays you can track with Google Scholar citations on papers. All of a sudden it's like, it's like explodes, right? So there was like a 25-year delay between the publication of the paper and when it started being appreciated. So maybe that can lift your spirits when you start publishing it. People aren't recognizing your work. Anyway, so I'm going to tell you about it, and we're going to use something called the CHSH Game, which is essentially equivalent to what Bell did, and it formulates the theorem as a game. So it attempts to make it fun. Okay. So the game looks like this. There's a referee And the referee picks 2 bits randomly, X and Y. Okay? That's the first part of the game. And then in the second part of the game, Alice and Bob have to reply with bits. We'll call them A and B. Okay? And they win the game if the logical and of the inputs is equal to the exclusive OR of the outputs. Right? So that's the game. So really to illustrate this, I'm the referee. Okay, so I have 2 points. Right? Flip both of them. To Tristan, I give 1 point. To Roy, I give another point. And then y'all have to be spatially separated, and ideally in like different rooms. Right? The point is, you can't communicate once the game starts. You're told what the game is beforehand. You can come up with all kinds of strategies. You're allowed to share randomness beforehand. So like you could have the outcomes of random point loops beforehand, or you could share a quantum state, right? But the shared randomness is what we call classical strategy. The quantum state sharing is a quantum strategy. Okay? And then once you have the coin flips, you have to report back. You could like raise your hand or something, right? And
Wait, what the
exclusive OR. So this means if you win, if and only if both coin flips are heads, like they're both 1, if exactly one of you raises their hand, not both, or not none. Let's look like this. Right. So exclusive OR is binary addition. Right. I'll just write it out. Right? So I mean, it's the usual addition, but then sorry, usual addition, but then something funny happens when you add 1, right? You get back 0. Okay. So that's the winning position. But, you can think of it in terms of the hand raise. It has to look like that. Not like this. Okay. So I didn't bring coins, but you can play the game, and you'll find that if you're not cheating, the best you can win is 3/4 of the time. Okay. And also, I'm assuming that the referee is the coins are fair, right? So like the probability of getting any configuration of the coin outcomes is 1/4. Okay, because there's 2 coins, 2 bits, so 4 outcomes, 1/4 fair coins. Okay, so what you'll find is that with classical, okay, and then with quantum, there's a significant difference in the winning probability. Cosine squared probability, famous number in quantum information, approximately 0.85. That's the winning probability. Wins with probability, cosine squared probability. Okay, what are we going to do today? We're going to prove that this is the optimal winning probability for a classical case. It will be left as an exercise. I'll give you a strategy for the quantum case. It's the well-known famous strategy that wins with this probability. That will be left as an exercise to like use the Born rule figure out what the winning, that that's the winning, to confirm that that's the winning probability. And then we'll also prove that this is optimal for the quantum tools. We can't do any better. Okay? That's the goal of today. We'll see how we do. Any questions about the game? All right. Let's proceed. This right here will be an indicator function telling you when they went. So, an indicator function is 1 when they went. So if this condition is true, let's call it, let's write it. Okay, and 0 otherwise. All right. So the strategy that Alice and Bob employ will correspond to a conditional probability distribution. Probability that they choose A and B given that they received X and Y. Okay. And what we're going to do for a classical strategy is impose certain constraints on this conditional probability distribution that are natural, based on the constraints that y'all are spatially separated, acting independently, that any prearranged strategy is independent of the choice of X and Y, right? That was something we said. We'll make that assumption. Those are really the two main things. Independence of X and Y and this locality constraint. Okay? All right. And the prior probability for X and Y, we said is uniform, right? 1/4. Question. So what is the winning probability? It's going to be we defined this indicator function so that we can have an easy way to write down the winning probability. So it's just the expectation of the indicator function with respect to this joint distribution. That's the winning probability. So it's just a sum of all the probabilities in the cases that they win, right? And the 1 picks out the probabilities where they're winning, and the 0 discounts the ones where they're not winning. All right. So the winning probability is going to be 1/4 the sum over all these indices, B, A, B, X, Y, and the conditional. Just to be clear, the joint distribution, this stuff, the joint distribution is the conditional times the prime. So that's what we're using and deriving this expression. Okay, so if y'all were using some shared randomness beforehand, that's what we call hidden variable. So we look in the physics literature, this term hidden variables. That is always called lambda. I believe Ms. Bell chose that. Lambda. So you can use the law of total probability to expand this distribution in terms of we can allow lambda to be a continuous variable. Lambda. that's just using a basic fact from probability theory. So lambda is a hidden variable. Okay. This, I think we know this, right? Okay, so as we've considered things now, we're to use like a block diagram to describe what's going on. Like the X comes in and it's copied and fed to X and Y are like copied and fed to this conditional probability distribution, which we can think of as like a classical channel. Right? So that's going to be this box. Out comes lambda. And then that gets fed to this channel, which generates A and B. Right? But this is a general way that you can expand the conditional probability distribution EAB given X, Y, but it doesn't correspond to how we describe the game. There are more constraints on what y'all can do. Right? So what are the constraints? Well, we said that lambda was a strategy. You have a question?
Yeah.
We're about to get to that.
Oh.
So here I'm using a general mathematical statement where, if there's some hidden variable, we get the original distribution by marginalizing over the hidden variable, right? Like, I think you know this, right? Like, if lambda were discrete, we would take the joint distribution and marginalize over lambda, right? And then you could factor this in terms of conditional probabilities like this. So we're using this fact to then now condition on X and Y also. So you can condition all these expressions on X and Y and it's still true. And then we made the sum and integral. So we're using a very general mathematical fact. But as you rightly point out, you're like, hey, this is not how the game was specified. So we're about to put more constraints on this and on this. And the first one is exactly what you said. Lambda cannot depend on X and Y. So let's just write that down. Lambda is, let's call it pre-shared randomness. Independent of X and Y. So that's a key assumption. And what does that mean? Well, mathematically, this distribution, P of lambda, in X and Y, just is P of lambda. Lambda has no dependence on X and Y. Okay? So that's the first constraint we impose. And again, that corresponds to y'all being able to know what the game is beforehand, talk about whatever you want to do beforehand. Then once you're in the room, the game is fixed, and a random, unpredictable X and Y comes along. Okay. So once we do that, the diagram and the mathematical expression change. Let's do both of them. So diagram now will look like this. And and then this expression will become, I'm not writing the commas, technically there's supposed to be commas. The next thing is we said that y'all are spatially separated. You're not allowed to cheat, you're not allowed to look at each other, you're in different rooms, no secret communication line. The way this gets enforced experimentally is through spatial separation, which you can't even signal fast, you can't signal fast enough to speed of light. Put each other far enough away that you wouldn't be able to send a signal. Okay. So because you're spatially separated, that means that this bot, you cannot act jointly. Like, it's like Alice is supposed to be, I'm drawing a line here. Alice is supposed to be up here and Bob is supposed to be down here. And so they can't do a joint action, right? So the point next is that this distribution has to factor, okay, due to locality constraints or spatial separation. Whatever Alice does is independent of Bob. So this distribution here has to factor into two distributions. I'll call one P. So I'm kind of doing two factorizations. Why don't we write them down properly? So we'll do this, and we'll split this into two steps. So it's really EA given lambda x and y. So these outcomes are independent. Okay? But furthermore, the diagram really has to look like this. Lambda is classical in copy. Alice gets a copy, and Bob gets a copy. There's X and Y. And then, whatever Alice does is confined to her lab. And whatever Bob does is confined to his lab. Okay? So this first factorization is just saying that A and B are independent given lambda X and Y. But we need to make a further constraint that A can only depend on X and lambda. It cannot depend on Y. Otherwise, that's cheating. That's like, Roy sending to Tristan Y over to the other room, and that's cheating. So we have to have a further factorization. And then once you do that, that's the final constraint. So this is the form of a classical strategy. I'm going to use P for both, but it's kind of an abusive notation, right? Because these are different distributions generally. So you just have to remember that, because they have different indices, they're different distributions. In the notes, there's all these subscripts indicating random variables. And P lambda. Okay. What do you see here? This is a convex combination. Here's the probably lambda of product strategies. Right? This is how separable states were kind of discovered. Okay, so Bell wrote down that this is the form of classical strategies. And then in 1989, Reinhard and Werner said, oh, if we have a separable state, which is a convex combination of product states, and then we did local measurements on that, the only kinds of distributions we can get are these. Okay? So that's the connection between separability and these local distributions. But Werner's paper was about more than that, that there could be some entangled states that still admit a local description, even though they're entangled. Right? But that's a separate discussion. We'll do that today. Okay. What I want to argue now is that we're doing all this business with allowing shared randomness, talking about we're trying to discuss the most general classical strategy. But what I want to prove now is that that will not do any better than simply a deterministic strategy, where every round you just report the same values. Or no, you report, rather than having a stochastic function that you do, like, if you get X, you might randomly pick some way for A. So what we're going to argue now is that actually you don't need to do that. You might as well just have a deterministic function from X to A, and that will do just as well as a randomized strategy. Okay? It has to do with the linearity of the objective function, the winning probability. Okay? So that's what we're going to see. Right, but this is the most general form of a classical strategy. Okay. Right, so what I want to argue next is that for this distribution, probably of A lambda X, so that corresponds to this part of the diagram. What I want to argue, I'm not going to give a definitive proof, is that here's lambda box. This can be simulated by a process where there's like a noise random variable, X, lambda, and then this is a deterministic function. And that can realize this classical channel. We actually just talked about the Stein-Spring dilation theorem for quantum channels. Okay, there's a version of that for classical channels. So what does the Stein-Spring theorem say? It says in the quantum case, you can introduce an environment in a pure state and do a unitary interaction. The classical version of unitary is just a deterministic function. And then trace out the environment, discard the noise. So what I'm saying here is that there's a classical version of that where we're preparing an environment in a noisy state, a noisy random variable. We do a deterministic function of these, and then that can simulate this classical channel. Right? So that's what we're saying, and that's kind of the justification I was good for it. I believe that the Stein-Spring theorem itself actually justifies it. The classical version of Stein-Spring. Okay. So what we're saying now is that, and then the same can be done for this, right? So we can have lambda y b M of a deterministic function if B. Okay. Right. So mathematically, what's happening is that we're saying that this whole distribution AB given XY. We have the expansion from before. I put the P lambda over here. But now we're going to expand each of these. Dn, and I'm going to call this F tilde. F tilde is going to be the probability distribution corresponding to this function. So if it's deterministic, you know, it's a degenerate probability distribution with all zeros in one somewhere, right? So, but it's chosen such that it realizes the function, right? So, here we're saying the function is f n x lambda equals a, right? And this probability distribution is such that when this condition holds, there's a 1, right? And if it doesn't hold, then it's 0. It's similar to this indicator function, this function, the relationship between these. Okay? That's going to be f tilde. So that's a given lambda, x, and n. And we're now, let me back up. We're going to use this kind of expansion using the law of total probability to require probability distribution and then the F tilde. A with lambda x and n. That's what we're using. Okay. Over here we have P of n. And then we'll do a similar expansion for the other term, which is this one. So Vm V tilde is defined in a similar way. Right? It's like an indicator function of a function P. V given lambda. Right. So that's a substitution that we're making for this conditional distribution and this one. Making substitution. All right. But if you rearrange terms, we have three integrals. We have dn, dm. What I want to do next is say, well, actually, this stuff in the environment that's independent of x and lambda, so that's n and m, that can just be part of a hidden random variable. Like they can be grouped together with lambda. Right? Let's draw a whole diagram at the end to try to clarify what's going on. But it's part of Bell's argument. Okay. So this was our final diagram before. And then now we're saying we can rewrite it. X. So external noise, deterministic function, F. Here's X. Let me put X in the top. Here's lambda. All right, so we're saying that this process can be simulated by this one, where f is a deterministic function, and so is g. Okay? And these f tilde and g tilde are indicator functions corresponding to those deterministic functions. All right. This is the hidden variable. And now what we want to say is, well, since this is like extrinsic noise, independent of X, M, and lambda, and the same is true for M, let's just group all this together and say, this is the new lambda. That this is all a hidden random variable in the background, right? That's what we're saying. Is that right? So grouped with lambda is N and M in the background. This is how we get from randomized strategies to deterministic ones. Because what you see with this is that a randomized strategy is simply a convex combination of deterministic product strategies. That's the conclusion that we're making. Okay. Good. Still good? Still plenty of time. All right, so let's go back to, this is the objective function that we're trying to optimize, the winning probability. Let's return to this. I want to group lambda and M together and call it lambda prime. Right. And then I want to rewrite this as P lambda prime, P lambda prime. So P lambda prime is just all these probabilities. Right? And now we're going to do a final redefinition. F prime will be A given lambda prime and X. And G prime will be B lambda prime 1. Right, so those are just some kind of rewritings. But what this means is what we said. A classical strategy can be written as a convex combination of deterministic product strategy. Okay. So let's write that down. So it's convex combination of deterministic strategies. Okay. So now I want to substitute into this winning probability expression 1/4, all this stuff. And then the next thing we do is a common mathematical trick, exchange the sum and the integral. Right? What is the interpretation of this when we did this exchange? The interpretation is that the winning probability is the average winning probability of these deterministic strategies, right? This right here is the winning probability of a deterministic strategy using F prime and G prime. Those are indicator functions, and they have, you know, particular deterministic functions corresponding. Right. So this is the average of winning probabilities. Right. And so next we use a basic fact. The average is less than the maximum. Right. The expectation of a random variable is less than its maximal value. Right. That's kind of a basic fact, right? Like, I can illustrate that mathematically. I mean, if you haven't thought about it before, it's worthwhile to write this down. Let's see. No, it's fine. Yeah. So there's some value, call it X max, that among the values in the random variable can take, it takes the largest value, right? So all we're saying is that, oh, this expression can be bounded from above by taking X, bounded from above by X max, which is the largest one. Now this is a constant independent of the sum. You take it out, and then you're summing the probability distribution. That's all we're saying, right? The average is less than the maximum. So we want to use that now. So among all of these deterministic strategies, they depend on lambda, right? So it's like some pre-shed randomness is chosen in the background, then based on the value of the randomness, we're doing some deterministic strategies. So we're saying among all those deterministic strategies that depend on lambda, there's one that will achieve the maximum. There's one or more that will achieve the maximum winning probability. We're just saying, okay, bound that from above by using this reasoning. And call the maximum value lambda star, right? Lambda star. So all this was just to conclude that, you know, there's some deterministic strategy that does the test. You might as well use that. Does anyone know what it is? We've done a lot of symbol pushing and moving things around, but in the background, you think about a deterministic strategy that wins. We said beforehand, we haven't proved yet, but we said that the maximum winning probability is 3/4. What is a choice of A and B? You can always report it down. It saturates the winning probability. Always return what? 0? Sorry, what did you say? I can't hear you.
So you're given X and Y.
You're given X and Y, yeah. Return X and Y. Okay. Let's work out how that would do. So X, Y. Here are the possibilities. 0, 0, 0, 1, 1, 0, 1, 1. So the and is 0, 0, 0, 1. If you returned X and Y, what is the or? There's the or, it'll be 0, 1, 1, 0. So then you would only win 1/4 of the time because the winning condition is that this has to be equal to that. Is it?
It's exclusive.
Exclusive or, yeah. Right. So like here's X and Y. These are the 4 values. Right. This is the and then this is the exclusive or. And then these are only equal to this entry. Not X and Y. All right. There's something simpler, but let's see. All right, all right. So not X and Y. I don't think that's like H does it not.
Zero.
Zero always. That does it. All right. All right, but not X. All right. I think that just flips. It doesn't flip anything, right? Because this entry goes to that and you swap, but then the exclusive order will still be the same. If you have like one of them, anyway, the simple strategy is to return all zeros. So if they just ignore what X and Y are and return all zeros, then the exclusive OR of all zeros is zero, right? And then 3 of the entries are 0. And so they'll get a match 3/4 of the time. So the classical strategy achieves 3/4 is to report that A equals 0 and B equals 0 all the time. Right. So that's a classical strategy. So far, what have we proved? I took you on a bit of a detour for this, but that was just good to think about it in a different way. We've proved that 3/4 is achievable. That's an achievable winning probability, right? We've also proved that it suffices to do a deterministic strategy. There's always a deterministic strategy that does better than a randomized strategy. Okay? And that essentially has to do with the linearity of the objective function that we could use convexity to conclude this statement. All right, now we have to prove that a deterministic strategy cannot do better than 3/4. All right, so let's do that now. So then with the achievability combined with the upper bound, we know that the classical winning probability is 3/4. All right, so what does a deterministic strategy look like? Well, if the input is X, you output some value of A that depends on X, right? We could write like A of X. This is like a shorthand for A of X, right? A deterministic function. Okay. And then Y goes to A of Y, just a shorthand. All right. Now let's enumerate this kind of truth table for a deterministic strategy. X, Y, 0, 0, 0, 1, 1, 0, 1. So the end of the inputs. 0, 0, 1. Now this last column is AX plus BY. All right. So what goes here is A0 plus B0. That's what they output. They output, you know, if Alice gets X equals 0, she outputs A0. And if Bob gets Y0, he outputs B0. And then we're computing the exclusive OR because we're going to be testing the winning condition. Right? They win if this is equal to that. Okay. And then B0 plus B1. 0. Okay, so now the question is it possible to have values of ax, by such that all four equalities can hold at the same time? Is it possible for that to be true? Suppose it's possible, okay? Then it would be true that if I added all the entries in this column and all the entries in this column, we would have equality because all the individual equalities hold. Right, so let's add column 2, add column 3. So if we add column 2, we get 1. This is binary addition. We're doing binary addition. Okay. Now look what happens if you add all these columns. All the entries in this last column. Each entry appears twice. When you add a binary number to itself, you get 0. They all cancel each other out. And so when you add column 3, you get 0. And of course, 1 does not equal 0. So the point of this is to say it is not possible to have deterministic values for A and B such that all four of these equalities can be satisfied at the same time. What Yvonne proposed is a solution that holds for 3 of the entries, for 3/4 of the time, right? So if we choose all of them to always be 0, right? If we choose function ax is 0, by is 0, well, then you see this is 0, this is 0, this is 0, this is 0. And so they'll match 3/4 of the time, but not that 1/4 of the time. So anyway, the conclusion of this is that it's not possible to satisfy with a deterministic strategy to win all the time, but only 3/4 of the time. So that's the upper bound on the winning probability. Okay, so this contradiction implies that the winning probability is less than 3/4. And then if we choose this way, we can saturate that upper bound. We're essentially out of time. Let me tell you any questions about this. So just to summarize again the whole development. We started out, specifying the game. We said that a strategy of Alice and Bob corresponds to a conditional probability distribution. We talked about the rules of the game. And we said you were allowed to have shared randomness beforehand. And the rules of the game imposed a structure that we said could be simulated by a structure like this. F and G are deterministic strategies. This is local noise. This is local noise. This is shared noise, shared randomness. These are the values coming in from the referee. These are the outputs. And then we argued that due to the structure, a deterministic strategy can always have the same performance or better than a randomized one. So it suffices to look at deterministic ones. Then we proved that the winning probability for the deterministic strategy cannot exceed 3/4. I think we should postpone the quantum part until the next one. All right. So next time we'll talk about a quantum strategy, and then we'll give the upper bound for a quantum strategy. The upper bound for a quantum strategy is called Tsirelson's bound. Oh, Tsirelson's bound. Boris Tsirelson. And it's his famous bound. His work was also ignored. He published in the 80s, and it was people working on quantum information, this and that, that discovered his work in the 90s. And then Shut up. All right, so I'll see you Monday. Enjoy the rest of your week.